Okay, so we talk about the derivative, and for just a regular function from R to R, the derivative, as we said, is a limit, and this represents the slope, basically, of what we call the secant line. We're trying to get the slope of the tangent line, which means we're trying to get it's also called the instantaneous rate of change of the function. So hopefully this is clear. You know this already. And there's a limit in there. So it's the limit of a slope as the denominator of the slope gets smaller and smaller. Of course, the numerator also gets smaller because of that, but there's some kind of ratio that they approach, and that is the derivative, and that is the slope of the tangent line. So just to remind you, this is not a very good picture, but suppose we have a parabola and we want to know the slope of right here. So we're talking about the slope. We mean that if we imagine that there's a tangent line there, the slope of that line, and the derivative gives us that. And the way we get it is by using a limit. So I'm not going to go through that now. On the other hand, suppose we had a graph that looked like this. We would say that there's no slope here. There's no tangent line here, so there's no slope. So we'd say at this point, this function is not, we could say it's not differentiable. So the derivative exists here, it exists here, so this function is differentiable actually everywhere. This function is actually differentiable everywhere except for just at this one point. But we say it's not differentiable there, because there's basically no unique tangent line there. So f is said to be differentiable at a when this limit exists. Okay, now we go to more what is this, a multivariate function, but it's still vector valued, or I'm sorry, still scalar valued. It's a scalar valued function. And we're going to define something called a partial function of this function with respect to just one of the input variables. So this has n input variables. So we're going to talk about something called a partial function of this function with respect to just one of the input variables. So what does that mean? It means, so this one would be, so we're going to use, for the notation for the partial function, we're going to use a capital F. So like little f is the function itself, and capital F is this, what we're going to talk about is the partial function with respect to one of the input variables. So this is going to be the partial function with respect to the ith input variable. And what does this mean? It means take this function and basically eliminate all the variables except for the ith variable, the ith input variable. So just set all the other ones to constants. So a sub 1, a sub 2, this means constants. It just means set them all to constants except for this. So now, so this function is a function of just one variable, whereas small f was a function of many variables. So, but this function, capital F, is just a function of x sub I. All the other ones we replaced by, all the other variables we're replacing by constants. And when we do this, this is called a partial function of f with respect to the variable x sub I. So let's try it and see, make this a little bit clearer. So suppose we have a function of two input variables. So function of two input variables means n is equal to 2. And so here it is. And now we're going to create a partial function with respect to just the x variable. So this was a function of x and y. So that means we're going to treat y as a constant. So we're going to fill it in with some constant and not think of it as a variable anymore. So the only variable that's left is x. So when we fill in y with some constant, like call it a2, then this becomes a2 squared and this becomes a2 squared. So we have that. And this is now just a function of x. So this is called a partial function with respect to the variable x sub I, in this case with respect to the variable x. Now, I guess the reason we use the word a instead of the is that we could we could choose different a's here, so they're all, given any particular a that we choose, we get a partial function. So there's more than just one. But anyway, what is this? Actually, when we do that, and we notice what we get, we actually just get x squared over x squared, which is just 1. So the partial function, now I guess that we're using the, because we see that no matter what a we put in here, it doesn't matter. Oh, I'm sorry, wrong. Sorry. If a is equal to 0, then this and this are 0, and then we get 1. Sorry about that. Okay. Then they say geometrically this partial function is nothing more than the restriction of f to the horizontal line y equals 0. That is, of course, if we make a equal to 0, if we make y equals 0, then we're just talking about this function. We're only thinking of the domain as along the x-axis. Note that the origin is not in the domain of f in this case. So 0 should not be taken to be the domain of capital F either, right? For this function, we can't put in, or actually for this function, we can't put in 0, 0. We can't put in the origin. Okay, let's read this remark. In this book, in practice, they don't usually go to the notational trouble of explicitly replacing the x sub j's with constants when working with partial functions. Instead, make a mental note that the partial function is obtained by allowing only one variable to vary, while all the other variables are held fixed. Okay, so now this is kind of taking us towards talking about derivatives for multivariate functions, and we've sort of taken a multivariate function and made it really into a bunch of single variable functions, single inputs. So that's what this partial function does. We start with a multivariate function with Rn, but we sort of break it up into these partial functions where we only have one variable, or one input variable. So then we can easily talk about, at least for these partial functions, we can talk about their derivatives. Right? We just use the normal concept of derivative. It's really just a function of one variable, so we can just use the normal concept of derivative. And in this case, we talk about the partial derivative of f. Now f is still that multivariate function, but we're going to talk about the partial derivative of f with respect to xi is the ordinary derivative of the partial function with respect to xi. So we'll use this notation for the partial derivative with respect to xi, and it just means the derivative. This symbol means the derivative, but the only variable is xi, and what this means is the same thing. It's the f, well, it's this part minus this part, and we only add in the h to one variable, to this one variable, and we divide by h, and this is called the partial derivative. So one way to think what I think of it when I think of the partial derivative is just that all the other variables are not changing, and we're only moving in the x sub I direction and asking what's the rate of change. But we can use this concept of partial functions to write it down. So this picture might make it more clear. So suppose we have this surface, so that's a function of x and y. And so what the partial derivative is for example, in this picture, which is being held, y is being held constant, right? Y is being held constant. So we're like y equals b. So we're only, basically we're talking about cutting this surface with this y equals b plane. So we just get this curve. And then we just have a curve in this plane, in this y equals b plane. And then we can just talk about the derivative of that. So this is the case where we have two input variables. Now, of course, if we have more than two input variables, we can't make a picture of it, but we can still do the same thing. We just hold everything else constant except for one of the variables, and that's what we mean by the derivative with respect to that variable. Or then we can talk about the derivative with respect to that variable. And here's the other holding x fixed. So setting x equal to a, for example, we'll slice the surface like this, then we're going to get this curve, and then we can find the derivative of that curve, and that's called the partial derivative with respect to y, because only y is changing, x is fixed. So it's very easy to do partial derivatives. For example, here's a function of x and y. If you want to know the derivative with respect to x, that means you hold y constant. So you just treat y as though it were constant. So like instead of x squared y, you might think, oh, there's a 5 in front of this x squared, and there's no y here. What's the derivative of that? What's the derivative of 5x squared? That's easy. And here, you'd say, okay, I'm going to hold y constant, so this is like the cosine of x plus 5. And then what's the derivative of that? Well, that's hopefully not too difficult either, but we're not specializing in derivatives of cosine, so we won't worry about that too much. But so the partial derivative with respect to x is when you hold y constant. So this term will be 2x to the first, and then the constant y, so to speak. And this term will be this one. And then we can also do the partial derivative with respect to y. Okay, this example is, notice that this function is not defined as 0, 0. So they say we'll use this formula for everything except for 0, 0, and we'll define it as 0 at 0, 0. So a kind of artificially constructed function. And we might ask, what's the partial derivatives? And we have to break it up into different pieces. You can read this. I'm not going to go through that. Okay, so jumping back to here, we gave a kind of meaning for differentiable at a, means that when this limit exists. Remember, sometimes limits exist and sometimes they don't. So if this limit exists, we call it differentiable. Now, another way to view differentiability is that you have a function like this blue curve, and we say it's differentiable at this point, means that there is a unique line, tangent, at that point. So if you imagine, if we consider this function, which is like actually the absolute value looks like this, but anyway, if we just consider this function, it's not differentiable at this point because there's not a unique tangent line. So differentiability, so if you did that limit, and I said that the definition of differentiability is that the limit exists, the limit wouldn't exist at this point. You could work it out and you could see that the limit would not exist. And another way to to understand that is that in order for it to be differentiable, there has to be a unique tangent line. So they say differentiable at a number means that the graph of the curve has a unique tangent line. Now we can ask, well, what is the equation of this tangent line at this particular point? And you should be able to figure that out because you have a point. And usually we say we want a point. Usually say we want 2 points to get the equation of a line, but we can also have 1 point and the slope and get the equation of a line. And since we know the slope, it's just the derivative. We'll just call it, whatever the slope is, we'll just call it the derivative because that's what they're the same thing. So we are assuming we have the derivative. Then so you have this you have a point and you have a slope. You should be able to write the equation for this line. It's a simple thing to do, and this is what you get. So here's the slope, and I'm not going to go through this, but you should work it out actually. But it's a very simple thing. It's just finding this. You have a point and slope. You should certainly be able to find the equation of such a line, and this is what you end up getting. So you can see that it contains a and f of a, so it contains information about the point, and it also contains the slope. Now, this seems a little bit weird what they're going to say next, but we're going to repeat it in a multi-dimensional case, so they want to do it in the single-dimensional case, sort of to get us on a kind of easy, firm ground before we look at the complicated case. So they just say that if you set h equal to this is some function of x. If you set h equal to that, then there are 2 things we can say about h. First of all, remember h is basically this line. So this line and this blue curve don't agree everywhere. In fact, they don't really agree. They only agree right here, in fact. They both have the same, they both contain this point. So that's what this says. H of a is the same as f of a. And the second thing is that the slope of this blue line is not the same as the slope of this line. At least not everywhere it's not the same. But certainly at this one point, the slope of this line is the same thing as the slope of the blue curve there, because that's what we mean by the slope of the blue curve there. So that's what this says. This says that this h prime, that gives you the slope of this black line, is equal to f prime, that's the slope of the blue curve. They're the same at a, not anywhere else, or not necessarily at anywhere else. It doesn't look like, is there anywhere else where it's the same? Not on this curve. If the curve went back up and came down, there might be another place where it's the same, but basically it's not the same, but it is the same at a. So we want to make these 2 statements here because we're going to say similar things in a more complicated scenario. Okay, so this was all about just plain single variable calculus. Okay, now we want to move on to a more interesting situation, where we have a function from R2 to R. So that's a scalar valued function of 2 variables. So and x is some part of R2. That's the domain. And so we're going to get the graph of this function f is a surface. So what we want now is similar to, we want to talk about the tangent line. We talked about the tangent line here. So we're talking about a surface, not a tangent line. We don't want to talk about a tangent line at a particular place, but we want to talk about the tangent plane at a particular place. So like here's the surface, and we want to ask what's the tangent plane at a particular point. Now the reason we're doing this is because, which is more complicated? Let's go back to the simple example. which is more complicated? F or the tangent line? The tangent line is much less complicated. It's just a straight line. F could be some crazy function. The tangent line is just so. But we say that the tangent line is an approximation to how F behaves just at this one little point. So it's much simpler to deal with, but it is some kind of approximation to F. And in the same way, which is more complicated, this blue surface or this tangent plane? Well, the plane is generally less complicated or simpler than the blue surface. And we can say that the plane approximates the behavior of the surface near this particular point. So that's why we're doing this. So here she says, what should the tangent plane to the graph of the function to the surface at the point? So what is the point? We're at some particular point. So how do we describe some arbitrary point? So remember, we're going to put in an A and a B. So we're going to specify some x is equal to A, y is equal to B. And we want to know, and then the height is what? F of AB. So that's the z coordinate. So this is the point. That's a way to identify the point. We're saying, what's the tangent plane at some point? So geometrically, the situation is depicted like this. So we're going to try and answer that by kind of step by step. So what we're going to do is we're talking about a plane at this point, and this is the surface, and we're going to take. So we're going to cut this surface with the plane y equals b, and we did that before when we were talking about partial derivatives. And we're also going to do it with x equals a. We're going to cut it. Now when we cut it with, which one are we going to do first? We're going to cut it with y equals b. So we're going to get some kind of curve in this y equals b plane. And then we want to write an equation for the tangent line to that curve at this point. So it's kind of complicated. And we want to write the equation of that line using a parametric equation. Remember, we learned about parametric equations. So they say, if we go back to section 1.2, so I'm going to go back there. So going back to here, we have this situation here. So the vector parametric equation for the line through the point P, this point, whose position vector is this, and parallel to the position vector of P0 is this, and parallel to A is this. So remember the picture here. So we have a point P0, and we want to get an equation for the line through P0 and parallel to some vector A. So we're given a point P0, we're given a vector A, and we want the equation of the line, of such a line, the line which goes through P0 and is parallel to A. So we want the equation of this line here. So the position vector for P0 is called OP, and looks like this because the coordinates of P are B1, B2, B3. So it looks like this. And this says that if we want to get to another point P, not P0, another point P here, we take R of T is equal to this plus T times A will bring us to some other point here. So we have this equation. And just for a little bit more quick review, so this is a vector equation, and it can be expanded into three non-vector parametric equations like that. Three, what do we call them? Scalar equations. So we have that as well. So now going back to this picture, we're talking about cutting the surface with this y equals b plane we're getting some curve in this y equals b plane, and we are trying to get the equation of the line tangent to that, and we're going to do it in vector form this time. And it's going to turn out to be this, and this is the same as r of t, this is L of t, so this is going to represent some other point on the line, just like this was some other point on the line. And of course this has to be in 3D, so we have to have a point in 3 dimensions, or in other words a vector. Anyway, so, and then we had the b here, so that is the point, is the b. So our point is this point here, so there's that. So here's our point, here's b, was the point in the other example. And then we need TA, and remember that, so here's the T, that's there, and then the A, whoops, then the A is supposed to be a line, a vector parallel to our line. So how do we get that? So she says here, from our earlier observations, we know that the partial derivative, remember what we're doing here, we're in this plane, y equals b. So when we move in this plane, y equals b, y is not changing. That's the whole point. Y is always equal to b in this plane. So y is not changing. So when we move in this plane, we want to get a vector which is parallel to our curve. So, but we know that if we move 1 unit in this direction, what did we mean by the partial derivative with respect to x? The partial derivative with respect to x here. What did we mean by that? That is the slope as we move 1 direction in the x direction. I'm sorry, 1 unit in the x direction. That is how much the z component will increase. So this vector is parallel to that, because it says as we move 1 unit in the x direction and 0 units in the y direction, the z direction will increase by this much. So that is the vector, this vector here, that is supposed to be parallel to our line. So remember, A could be, there are many vectors that are going to be parallel to our line. It doesn't have to be this one. For example, if we went 2 units in this direction, we could just make this double, because we would increase by 2. But remember, we're not changing y, so this is 0. So that is our vector. So finally, we have this line, which is this is the vector equation of the line parallel. Sorry, this is the vector equation of the tangent line. Now, if we just want something which is parallel to this tangent line, then we just want this vector here, without the t there. So that vector has no no j component. It had one unit in the I direction, 0 units in the j direction, and this much in the k direction. So that's if we just want a vector parallel to the tangent line, it's 1 for I, 0 for k, j, so there's no j here, and then this amount for the k. So okay, so we're just doing this step by step. So now we have a vector which is parallel to this tangent line. And then we can do exactly the same thing, but using this plane instead of this plane. So remember, what are we trying to do here? We're trying to get the equation for this plane here. and we decided to sort of break, it goes kind of step by step. So what we found so far is we found a vector which is parallel to the tangent line in this direction, in the y equals b plane. And then if we want to do that same thing in the x equals a plane, we'll get this. So this is the only difference. I mean, the main difference here is that this is f of y. This was f of x. I'm sorry, why did I say that? This is the partial derivative with respect to x, and this is the partial derivative with respect to y. Okay, finally, both of the aforementioned tangent lines, this one and this one, must be contained in the plane tangent to z, must be in this plane at this point, must be in this plane if one exists, if there is a tangent plane. So both of these have to be there, right? We're going to get a there and this. Sorry, I think I said that wrong. Both of the tangent lines have to be, so this line and this line have to be in the plane. And therefore, a vector n normal to the tangent plane must be perpendicular to both u and v. Therefore, we can take we can get a normal vector by doing the cross product of u and v. Now, this won't work, I guess, when we're working in higher dimensions, because we don't have a cross product in higher dimensions, but it works here, right? So anyway, this n, this is going to be perpendicular to this plane. And the cross product of u and v, I guess we can do that, we can work it out, turns out to be this. So you can work that out. Okay, so now we have the normal vector to the plane, and we also know a point in the plane. And I know we did an exercise where we could find the equation of such a plane. If we know the normal vector and we know a point in it, we did exercises where we could get the equation. So hopefully we remember how to do that. And it says go back to equation 1 in section 1.5, and that will show us how to do it. So I'm not going to go back. I'm just going to assume that this is correct. Okay, or equivalently, so this is a dot product here. So equivalently, we can write it out like this. And then they say by rewriting this equation, we have shown that they just bring this z over to this side. So we now know that equation for the tangent plane for our surface at some particular point AB, and then f of AB is the z coordinate. So finally, we got the tangent plane. This is like having gotten the tangent line in the single variable case. So let's go back to the single variable case. Remember, we said this. So we did this just a little earlier, and we said that if we take our equation for the line and we set it equal to h of x, then h of x has these two properties. One is that it's got this the same height at A as the blue curve does, and that's the only point where it has the same height, but it does at A, and also the slope is the same at A. So what are we going to do now? We're going to take our equation for the plane, which will be like this, but it'll be the equation for the plane. We're going to set it to h of x, and what are we going to say? We're going to say that our plane is exactly at A has exactly the same height as our surface, but then this one's going to be a little bit more complicated. So let's see how it works out. So here's our equation for the plane. We're going to set h equal to this, which is h of xy. It's going to be h of xy now is equal to this. Then at AB, h has the same height as f does. And then the second part is that the partial derivative in the x direction is the same as the partial derivative in the x direction for f, and the partial derivative in the y direction is the same as the partial derivative of f in the y direction. So in words, or in other words, h and its partial derivatives agree with those of f at AB, and maybe only at AB, but at least at AB. Now she makes some technical point. She says you might want to make I guess make a theorem that if a surface has a tangent plane, that a surface does have, so a surface has a tangent plane as long as the partial derivatives exist. But then they say no, it's not quite enough, and they bring up this picture which has partial derivatives here and here, but we don't say that there's a tangent plane here. You might say that you can imagine kind of a tangent plane here, but you can read this. She says it's not, in a certain sense, it doesn't make sense to say there's a tangent plane. But anyway, okay, let's not get bogged down with that. Let's just say that this is the equation of the tangent plane if one exists, and if there is a tangent plane, then it has these two properties, 1 and 2. Now down here she says that this example, which is here, shows that the existence of a tangent plane is a stronger condition than the existence of the partial derivatives. So if you have a tangent plane, you do have the existence of partial derivatives, but not vice versa. And we aren't going to say that a function is differentiable. We can make up this definition of differentiable, and we're not going to say that a function is differentiable if its partial derivatives exist. We're going to choose the stronger condition, which is we're going to say a function is differentiable if it has a tangent plane. So it's differentiable at a certain point if it has a tangent plane. So we will come back to that next.